Okay, so this is a new topic we're looking at today, and this is the topic of scientific notation. Now, this builds up on what we did in the previous year's content in terms of numbers. And a big thing we did there was looking at rounding numbers. And we talked about rounding as expressing a number to some degree of accuracy, some degree of desired accuracy. And this topic, which is in the Stage 5 Year 9 content in Australia, I think, we take this one step further. And honestly, another kind of term I give this subject is really just humans are lazy. And you'll see why. Because scientific notation has spawned out of scientific studies looking at really big numbers and really small numbers. And when we look at these numbers, we want to express these in a way that we can interpret the magnitude of these numbers, sort of how big, how small they are, without having to write all of the digits. That's really the essence of this topic. Now, I've split this up into two videos. I have really big numbers in this video, and we will look at really small numbers in the next. Now, let's start. Say you were a scientist and you're looking at studies looking at the distance between the Earth and the Sun. So I have the Sun here. Really bad drawing, I know, but just bear with me. And we have the Earth here. In reality, it should be a bit smaller, I think. But I'm not really a scientist. We're just looking at the maths behind this. So I have the Sun and the Earth, and from what I looked at online, the distance here is roughly 150 million kilometers. Now, really big number. And a lot of science deals with these numbers of magnitude, we call them. These really big, really small numbers. Now, let me write this number out. So if I want to write, I've written it in words here, but writing it in numbers, 150 million. Now, I've used a smaller example here because I just want to show you how this works. In reality, scientists often deal with even bigger numbers. So, in essence, this number is annoying to write. It's annoying to write all these zeros. I've expressed this in terms of some degree of accuracy. I have estimated, I've rounded, and for some revision in significant figures from my previous video, this is to two significant figures here. Now, these two are kind of my digits in question, my significant figures here. And this number just has a bunch of zeros attached to it, right? And let's look at what the effect of these zeros kind of is, the kind of mathematical effect. Now, if we take, say, any number, right? If we took the number, okay, let's go the number 5, and we times it by 10, we would get 50. If I times this same number by 100, I would get 500. Times it by 1,000, I'd get 5,000. Do we see a pattern here? The number of zeros I have here, that gives me the amount of zeros here. Now, could we not then say that, well, all of these zeros here are just the effect of multiplying by 10 quite a few times? Let's go back to this example here, because 5 times 1,000, for example, is the effect of going, or 5 times 10 times 10 times 10. Because 1,000 can be broken up into a product of three tens. But think back to what we did in the year 8 content. We looked at powers and indices. And we can say that the effect of timesing 10 by 10 by 10, it's a bit tedious writing it like this. We have a tool to make this easier. We can write this as 10 to the power of 3. And that is exactly what we can do with our numbers of magnitude. Because this number here, get rid of this, that is the same as going, well, this is like saying that, let's say 15, right? That's 15 times 10 times 10 times 10 times 10 times 10 times 10 times 10. Let's rewrite this. It's like saying 15 times 1, 2, 3, 4, 5, 6, 7. This is like saying, well, 15 times 10, 7 times, right? And I write this now. I can write this as, well, 15 times, and all of this here, that can be rewritten like we did in the previous example. This can be rewritten as 10 to the power of 7. And that's exactly what I'm going to write here, times 10 to the power of 7. Now, I'm going to take this one step further, because 15 is like multiplying 1.5 by 10. Because the 10 would just shift. So let me do a little aside here. 1.5 times 10. The 10 would just shift my decimal place along to here. And I would get 15. So I can take this one step further and write that this is the same as saying 1.5 times 10 to the power of 8. Does that make sense? I've just added another 10 that I'm multiplying. Because this form here is the general way we express things in scientific notation. Because we're dealing with big numbers, especially once we round them to a certain number of significant figures, we're going to get a lot of 10s multiplying by each other. And we can express this using our indices just as 10 to the power of however many 10s we had. And it's customary for this number, when we write in this form, our 1.5, this number should be between 1 and 10. Because if we had anything more than 10, well, that's just the equivalent of multiplying by another 10, essentially. So the number we have here, that is going to be between 1 and 10, and we just multiply by 10 to the power of however many we have. Now, let's say we dealt with one more. I'll give you one more example. Let's say we call this example 2. Let me show you a kind of quick and easy way we can kind of do this. Because this way was to take it really slowly, give you some conceptual understanding of how we get to this here. But I'll show you actually in practice a more efficient way we can deal with this. So I won't use like a real world example because I can't think of any more off the top of my head. But let's just say we had this number here. Really big number. This number can represent anything. But as I said at the start, humans are lazy. We wanted to come up with logically and mathematically correct way of just expressing this with less work. because I don't know about you guys, writing this many zeros is really annoying. So here we have a bunch of zeros, and I don't want to keep writing all these zeros. If I'm writing a scientific report, it's going to be really annoying to keep writing this many zeros all the time. That's why we use scientific notation, because we're lazy. That's the kind of main takeaway here. So I can think of this as kind of some whole number here. Now, to convert this to scientific notation, I just want to find out how many tens got multiplied. And eventually, I want my kind of decimal, I want a decimal point to end up here, like you saw there. So I can think of my decimal point as being all the way at the end here. And I want to just get my two significant figures. I want this number in scientific notation to be between 1 and 10. So I will want this thing to end up here. And we just want to find how many spaces we went along to get from here to here. And that will tell us how many tens we actually ended up multiplying by. And I'll show you what I mean. So we can kind of hop along. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that got a bit messy towards the end there. But I found essentially how many tens we multiplied by. So I have now that this is 6.8, because we want the number here between 1 and 10, times 10 to the power of 11. And we can test this again, right? Because once we have our answer, we can check that we've done it correctly by just going back from scientific notation to writing the whole number. Now, 6.8 times 10 to the 11, that is like, if I multiply by 110, that is like saying 68 times 10 to the power of 10. And then I can just write 6, 8, and then 10 tens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you will see I have the exact same number of zeros. So I've done this correctly. Let's just count them to double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my scientific notation is a mathematically correct way of writing this. Those were just a couple of examples. Now we are going to look at going the other way in the next video. So instead of dealing with our very big numbers here, we're going to deal with some really small ones. I'll see you there.